Well, good afternoon, everyone. Clement told me already that right after lunch, it's always challenging to get people back in the room, and I can see that the room is not so full right now. But I hope you enjoy this presentation. And I want to thank Clement and the EASA team for inviting me to speak on this topic. And we'll talk this afternoon really about restoring practical IFR certification to single-engine rotorcraft and speak at some length on how that developed in the United States with the FAA, but also finishing up on what EASA has been doing in this area. So without further ado, also mention, some of you may know him, but this presentation is in honor of Eric Oldhayton. He was a Bell Tech Fellow for many years and passed away late last year. He was instrumental in working this on our behalf, also with the FAA. So the aim is to reduce weather-related accidents in the largest population of helicopters, 14 CFR or CS-27, 14 CFR 27 or CS-27 single-engine rotorcraft. The four things that we wanted to achieve with this was to provide a safe but cost-effective IFR solution for single-engine rotorcraft, provide helicopters that could capitalize on the WAAS capability that the FAA has invested in, also provide a population of helicopters that can operate in that space, and especially, lastly, changing the culture of rotorcraft operations to make the safety of IFR commonplace. To give you a little history, between the years 2000 and 2019, you can see here that for rotorcraft, starting with the smallest rotorcraft, compared to the smaller fixed-wing aircraft next to it, that we couldn't offer IFR capability until a pilot would get into a twin-engine, 6 to 8 passenger aircraft. So by the time a typical helicopter pilot gets to an IFR-capable rotorcraft, the culture of avoiding weather by flying beneath it is long established and entrenched. Let's look at the accidents for a minute and just the history of that from 2001 to 2013. These are accidents worldwide. And you can see there were 194 accidents related to inadvertent IMC or controlled flight into terrain due to low-level flight to avoid weather. 133 of these accidents involved fatalities. 326 people lost their lives, and 57 of these accidents occurred in the United States. Give you a little history here, and I won't read all of this, obviously, but to touch on it, in 2014, both in 2014 and 2015, the NTSB noted helicopter operations and public helicopter operations on their 10 most wanted list. In 2014, also, the U.S. Congress forced some new rules for helicopter air ambulance. The clear message for that was to encourage more IFR, to provide better decision tools, and also better tools when in trouble. So the environment was there to make changes and to start to make IFR and rotorcraft, small rotorcraft, possible again. What happened to single-engine IFR? Around the 1980s, there were a number of single-engine IFR-capable rotorcraft. These had the older analog systems for instruments, and in 1999, the FAA adopted numerical safety methods for safety analysis that really were from the 14 CFR Part 25 or the large transport category aircraft rules. Since that time, there have been many technology improvements. WAAS navigation, as I mentioned, ADS-B, in and out, GPS, LPV approaches, flight sensors, excuse me, synthetic vision, moving maps, and then autopilot, and also stability augmentation system technology, but no single-engine IFR since 1999. So, changing the helicopter culture. We start at the top. The issue really was the chicken and egg issue. What are we going to attack first? So we had a lack of helicopter conducive IFR air routes. We had very few helicopter pilots comfortable with IFR, limited opportunity for them to remain current, and also very few single engine IFR certified helicopters, single pilot IFR certified helicopters. So this is where we can break the cycle. Again, a little bit of history in the U.S. timeline. So in 2014, the industry associations met with the FAA Director of Certification at the time, Dorinda Baker, and she challenged the associations and industry to provide consensus recommendations to enable practical IFR, single-engine IFR certification. In November of that year, industry met to review a draft white paper. In 2015, a number of things happened. Another industry association, AHS, and now VFS, which is now VFS, joined. And the industry press joined in to support the initiative. And then it was a major topic at the International Rotorcraft Safety Forum in April of 2015. And in September, the industry published the white paper and addressed a number of areas recommended change. In 2016, in the beginning of the year, there was an initial meeting with the FAA. And then in the first quarter of that year also, the FAA began to draft a safety continuum policy as a response. The FAA committed in July of that year to releasing the policy, and in March of 2017 it was issued. Industry did comment that the policy didn't go far enough to restore practical IFR, with only 1 out of 6 areas from the white paper addressed. But in June, the safety continuum policy did come out, and then in November of that year, the FAA and associations met to find a path forward on the remaining items. And what was decided was that an actual applicant cert plan and the issue paper process would be used to set precedents. In January 2018, Bell submitted a certification plan for the 407GX to retrofit an IFR STC system on the aircraft, and that was the test case. We used the safety continuum and then proposed 5 white papers to address the other areas that hadn't been addressed specifically. The FAA responded to the cert plan, and the draft issue papers were submitted, and in September, Bell submitted another cert plan for the 407GXI. Moving to 2019, Leonardo received IFR certification for the TH-119, and in August, just a few months later, Bell received approval for the 407GXI IFR STC, and we promptly started selling aircraft, with 3 sold in the first month. So it's certified using the safety continuum policy, and it set the precedents for all but 2 of the white paper recommendations. Let's take a quick look now at where we were prior to the safety continuum policy, and then also where we are now. So you can see there, unlike the fixed wing aircraft, where you have different classes of aircraft within the Part 23 space, you had, for Part 27 rotorcraft, it was very similar to Part 25 transport category aircraft. Let you just take that in for a moment, because there's a lot of information on that chart. So what did the safety continuum policy allow? It provided for 4 classes of aircraft, very similar to the Part 2023 rules. And so based on the number of passengers and basically the class of different classes, for the smaller aircraft, the requirements for the safety analysis could be reduced, and thus we could reduce the cost and weight for IFR systems similar to fixed-wing Part 23 aircraft. So a summary of the white paper items as what we addressed and then what we also didn't address on the 407 GXI project. We had 3 alternate HERF means of compliance, mitigations for stability augmentation system and boost redundancy, and then also assessment of unrecoverable loss of all nav and comm. The things that we didn't address were a larger battery in lieu of a second generator, and we also didn't address the single pitot-static system. We'll go into a little more detail in each of these items, and I'll share with you what we did for them. So first, for the alternate HERF methods of compliance, of course, Part 23 airplanes have policy that allows the general characteristics to determine required equipment qualification. The only thing that was available previously to Part 27 helicopters and Part 29 helicopters was AC 20-158A, and that was really creating the same level of requirements as, again, 14 CFR 25, the large transport category aircraft. The issue paper proposed airframe, pedestal, and wiring construction-based credit for attenuation based on past test experience with similar designs. And then the FAA, of course, planned to use the safety continuum policy and issue papers from the applicants to set the requirements. Mitigations for the stability augmentation system and boost redundancy. So in case of loss of the SAS system and boost availability, the conventional thinking had been that redundancy is always required for IFR, but for this class of aircraft, dual SAS is heavy and expensive. It's also not practical to add a second boost system in mini rotorcraft. And this tended to be the biggest obstacle preventing IFR STC to existing models. The adjusted thinking was that rotorcraft certified VFR without SAS and single boost, they'd have to have a degree of visual cueing where continued flight and IFR is safe. So you can see there on the bottom the difference between the modern displays and the rotorcraft and the older style analog instruments. So provided mitigation to have large attitude presentation and synthetic vision. And also the boost had to have a reliable design and a history to support, since a loss of boost means no stability augmentation. What we did on the 407 GXI is that we actually had a flight test evaluation program. It involved 16 pilots and included FAA pilots, Bell pilots, and also some external pilots with varying degrees of experience. We assured an IMC experience by covering up the windows, the lower part of the windows on the rotorcraft, and then we did a number of test flights. It included en route IFR, changing of flight plan, instrument approaches, multiple, different kinds of approaches. And then we scored all those flight tests against the practical test standard as if flying with no failures. We even included a small stature female pilot to show that with the boost off, the aircraft was still easily controllable. Moving on to unrecoverable loss of nav and comm. So again, conventionally, this was considered catastrophic based on 14 CFR 25 guidance, which had been adopted for both Part 29 and 27. It was recognized as hazardous in Part 23, and for aircraft still able to, for Part 23 aircraft, for aircraft still able to dead reckon nav to likely VMC and a small emergency landing footprint that was deemed acceptable. And why would it be different for Part 27 rotorcraft? The same mitigation would seem to apply to these aircraft. And then HERF for catastrophic failure is an issue. So the qualification requirements then, of course, would be set by that. For the Part 23 market, lower cost and weight nav and comms were available. And so there was an opportunity there to also bring this into the Part 27 rotorcraft. The FAA accepted this for the 407GXI and our cert plan. So the things that are remaining, the larger battery in lieu of a second generator is one. That is a practical and required step for us to be able to retrofit the existing fleet. It's obviously often difficult based on the aircraft configuration to install a second generator, and it also adds a lot of weight. And again, the regs do allow for IFR with a single generator and a large battery in single engine aircraft, including turbine airplanes and helicopters. The guidance in AC 27-1B does place pretty onerous requirements on the battery in this configuration, especially the time that the battery has to provide power. So basically half the max fuel duration, which could be 2 hours. What happens then is the fuel capacity has to be reduced when the battery size becomes impractical. Ultimately, really, that results in a reduction in safety. Compared to the fixed wing requirements, obviously, also this was a much greater burden, where for fixed wing it's only 30 to 60 minutes, and it's not related to fuel capacity. Part 135 requires an hour assured power to carry paying passengers, and then our proposed method for that would be to placard battery duration targeting greater than 1 hour and limit IFR to 1 hour from a suitable emergency landing site without relation to fuel capacity. The last item is the single pitot-static system. Obviously, it's often difficult to retrofit and certify a second pitot-static installation. The dual heated pitot-static can significantly increase battery load, and the regs do allow for a single pitot-static system with an alternate static when single pilot IFR. So again, we could, it's common in IFR airplanes, and it used to be common in IFR helicopters, and I think the mitigations today are better than even in the 90s. Continuing on the single pitot-static system, the loss of airspeed indication, if recognized, is a manageable failure, but misleading airspeed due to a pitot problem is the real concern. If it's not identified, then it can be catastrophic. Icing is the most common source of in-flight misleading data, and blockage by a foreign object while in flight is pretty rare. So the design of the pitot probe can manage that, obviously, and the other last item that can lead to pitot problem is foreign matter blockage, and that can be insect activity and generally something like that, but that should be apparent before entry into IMC due to no airspeed reading. So the method is to have a redundant pitot heat power source and a robust monitoring design that would address the most realistic threat to prevent the remaining misleading state. So a quick summary of progress in the U.S. before we touch on what has been done with EASA and in the European Union. So first, the growth of IFR infrastructure, that is in place. There have been significant technological advances since 1999, as we talked about, glass cockpits, better, higher reliability sensors. We've got that in place. The FAA and industry cooperated to improve 14 CFR 27 IFR certification. Since we're not finished with all the different issue papers, I consider that still in progress. And then lastly, operator and pilot cultural change. It needs attention, but it will follow availability. So what we're looking for is enhancing helicopter safety through increased IFR helicopter operations. Now to touch on EASA progress in this area. So first, with respect to advocacy, the EASA Rotorcraft Safety Roadmap discusses the benefits of IFR, and that's been in place for some time. Yesterday here there was a workshop sponsored by EASA and EHA members to stimulate more IFR usage and projects and VTOL operations over Europe. Perhaps some of you attended that. EASA and the European operators are looking to promote IFR flying. And then there's also discussion with national authorities and operators how to improve acceptance and stimulate launching of projects. As far as rulemaking for EASA, unlike the FAA who put out a policy statement, rulemaking is the formal vehicle to provide for new rules. And so late last year, there was NPA 2021-11, and we're going to take a little more detailed look at that. So the intent of the NPA was to provide proportionate and cost-efficient rules in the field of the safety assessment provisions for equipment, systems, and installations for rotorcraft while we're maintaining a high level of safety. An additional intent was to increase harmonization of the safety assessment provisions for rotorcraft with especially the FAA equivalents, which are from the safety continuum. And then the NPA introduces proportionality in the safety assessment objectives, similar to that of the policy statement by having 4 different classes of aircraft. Additional progress, so again, kind of reiterating what I've already mentioned in part, the proposal to enhancement of the safety assessment processes for rotorcraft designs, proposing to change the acceptable means of compliance for CS 27-1309, introducing a safety continuum similar to the FAA policy statement. And as I mentioned, the AMC introduces the 4 classes of rotorcraft, allowing for proportional safety objectives based on the size and complexity of the aircraft, and that facilitates installation of equipment and technology that could improve safety. In summary, Bell looks forward to using the AMC to facilitate validation of single-engine IFR capability, and we look forward to continued EASA activity in this area to provide opportunity to improve safety for single-engine operations in the EU. Thank you very much.